In section 7.5, we're going to look at the derivatives of the remaining trig functions. There are 6 trig functions in total, and in 7.4 we discovered that the derivatives of sine and cos were each other. The derivative of sine was cos, and the derivative of cos is negative sine. What we want to do now is develop the rules for the derivatives of the other trig functions, so we'll start with tan. Now we want to find the derivative of tan x, and we already know how to find the derivative of sine and cos. And the nice thing about trig functions is that they often can be written in terms of each other. So if we look at tan x actually is an identity. It can be written as sine x divided by cos x. It's called a quotient identity. And now that we've expressed it in terms of sine and cos, we can now take the derivative using the quotient rule. So what we're going to do here is we're going to go dy dx equals, and then we're just going to apply the quotient rule. The derivative of the numerator would be cos x times the denominator, which is cos x, minus the derivative of the denominator, which is minus sine x, times the numerator, which is sine x. And all of that would be divided by the denominator squared. So that would be our derivative of tan x, but that's kind of an awkward expression, so let's see if we can simplify it. We have cos times cos, which is just cos squared. The two negatives become a positive. Sine times sine becomes sine squared. And then all of that, of course, is over cos squared. Now, you may recognize the numerator. Cos squared plus sine squared is a very common identity. It's called the Pythagorean identity. It's actually just equivalent to 1. So all of a sudden, things are getting quite simple. We now have 1 over cos squared. But I just do not have that fraction, so 1 over cos is also an identity. It's secant. So what we can do is we can write this as secant squared x. And that's how we take the derivative of tan. Now, instead of going through all this work every time, which a person could, you're better off just to memorize the formula. So the definition of tan will just be secant squared. There's going to be 6 definitions in total. This would be definition number 1. This would be number 2. And now we've just found number 3. Number 3 is the derivative of tan is secant squared. So let's try this now on a different function. We've just seen tan, so we've got the 3 primary trig ratios. So let's try y equals secant x. The trick here again is it possible to write secant x using one of the primary trig ratios? Well, secant is the reciprocal of cos. So what we can do is we can write this as 1 over cos x. Now, if I was going to take the derivative of 1 over cos x, I would have to use the quotient rule. So what we're better off doing here is moving the cos x to the numerator and writing it as a power to a negative exponent. So 1 over cos would be equivalent to cos to the negative 1. I can now use my extended power rule. So the derivative dy dx would be negative times, the bracket stays the same, subtract 1 from the exponent, times the derivative of what's inside the bracket, which would be negative sine x. And that would be your derivative of secant. But once again, it's possible to simplify that. That would be an awkward thing to try to remember. So the 2 negatives cancel and become a positive. The cos x is raised to the negative 2, so it would go to the bottom. So we would have 1 over cos squared x times sine x. And then what I'm going to do is I'm just going to rearrange this. The 1 over cos squared could be 1 over cos, and I could multiply the other cos underneath the sine, like that. And the reason why I want to do that is because I now can use identities. 1 over cos is secant x, and sine over cos is tan x. And there you have rule number 4. It turns out that the derivative of secant, it's kind of a unique derivative. It has itself, it's the first time we've seen that, the derivative actually has itself in it. It turns out if you have a secant x graph, the derivative would be secant x times tan x. Now we could repeat this for the other 2 ratios, but I'm just going to save you some time here and suggest that, first of all, on page 331 in your textbook, there's a summary of all of the 6 derivatives in one place, so you can refer to that if you need to. What I'm going to do here is I'm going to just write down the other two for you. So we would have, for number 5, we've looked at sine, cos, and tan, and now we've looked at secant. So we're going to have also y equals cosecant x. And again, the way you would do that is you would just write it as 1 over sine. But it turns out that the derivative, if you have cosecant x, it turns out that the derivative is negative cosecant x cotan x. And the last one, number 6, would be for cotan. If we had cotan x, then the derivative dy dx would be negative cosecant squared x. So those are your 6 derivatives. I'm going to now just for a moment discuss a pattern here. It'd be nice, a person does have to learn these, and it'd be nice to recognize a pattern. So I want to pair these up for you. Notice that the complementary functions, if you look at sine and cos, look how their derivatives relate to each other. One is sine x, and the other one is cosine. If you look at tan and cotan, which are complementary functions, notice that their derivatives are also complementary functions, secant squared and cosecant squared, with one being a negative. So there's a pattern here. These are complementary functions, the derivatives, sine and cosine, and these are complementary functions, secant and cosecant. And if you look at the other two, the same pattern is there. If you look at the derivative of secant, it's secant times tan. The derivative of the complement of secant, cosecant, is the complement of this derivative, negative cosecant cotan. Now, I don't know if that made any sense, but hopefully you might be able to arrange this into some kind of pattern. So all of the derivatives, if you look at the derivatives, we got sine, we've got secant squared, and we've got secant tan, and then the other 3 are just the complements, cosine, cosecant squared, and cosecant cotan. And of course, half of them are negative and half of them are positive. So hopefully you can come up with some kind of strategy, because you are expected to know the rules for the definitions of the 6 trig ratios. So now what we'll do is we'll just do a few examples. The good news about this is now that you've seen the derivatives of sine and cos, you understand what happens with the argument. The same thing applies for these questions, so we'll just do a few examples. Okay, so I have here 3 examples of 3 different trig functions, and we're going to find their derivatives. So in the first question, we have an argument change. The first question says f of x equals secant 3x. So the part you really need to worry about here is whatever the argument is never going to change in the question. The rule for secant, if you have y equals secant x, then the derivative dy dx is secant x tan x. That's the actual rule. But the part that's important here is that this is called the argument. And the argument stays the same regardless of what the function is. But then, of course, because of the chain rule, we have to take the derivative of the argument. So the way this would work is you would go f prime of x. And because you have secant, we would use this rule right here. And whatever is the argument just stays there. So this would be secant 3x times tan 3x. I think that's the most important thing that you realize, is that it doesn't matter what's inside the argument, it stays in your derivative. But you then have to multiply the entire function by the derivative of the argument. So in this case, that would just be times 3 because of the 3x. And then you're probably better off putting the 3 in front, just so it doesn't look confusing as to what's happening with the arguments in the question. So there would be your derivative. The next question is a little more complicated. The next question is a product rule. We have 2x times cotan squared 5x. Whenever you have an exponent with a trig function, I find it beneficial to, before you take the derivative, what I like to do is I like to write the question with the exponent like that. Then it's more evident to me that the power rule is being applied here. So what we have here is a function times a function, so we're going to have to use the product rule. So dy dx would equal, the derivative of 2x would just be 2 That would get multiplied by cotan 5x all squared plus, and now we got to take the derivative of cotan 5x all squared. So what dominates here is we have a power. So we're going to go 2 times cotan 5x all to the 1. Then we have to move inside the bracket and take the derivative of cotan 5x. Well, the derivative of cotan, again, if you just look at your rule, the derivative of cotan is negative cosecant squared x. So the derivative of cotan 5x would be negative cosecant squared 5x. Notice that the argument just stays the same. The argument doesn't influence how you take the derivative. If it's cotan, the derivative is still negative cosecant squared. The price you pay, though, is that if the argument isn't just an x, you have to multiply by the derivative of the argument. So that would be 5. And then don't forget we were applying the product rule. So we have to multiply all of this by 2x. Now this would be an unsimplified form. For our purposes of just learning this right now, we're not going to worry about simplifying it. So we'll just leave our answer in unsimplified form, and that would be your derivative. So I use this question because it combined a few things. How to deal with the power, an argument change, and of course the product rule. And then for our last example, just so you can see that we can combine the transcendental functions, in our last example we have the function f of x equals e to the tan x. Well, whenever you have any function f of x equals e to the x, the derivative, if you recall, is itself. So the derivative here, f prime of x, will just be e to the tan x. It's an interesting function. The derivative is itself. But you always have to take the derivative of the argument if it's more than just an x. Well, in this case, it's tan, so all of this gets multiplied by the derivative of tan. So again, if you refer to those 6 rules, the derivative of tan is secant squared x. In this case, I left the argument as just x to show you that in that case, we wouldn't do anything after that. If you want to see the big picture here, you still are taking the derivative of the argument, but the derivative of the argument in this case is just 1 because it's just x. And so we just tend to disregard that and only worry about it if it's something more than just an x. So that wraps up our study of trigonometry. The next section is 7.6, and you're not responsible for that. So the next video is going to be the review where we talk about the exam and what you're responsible for.